This year is Arthur Elsner, and he'll be doing a performance art piece called Perfect Paul and the Freedom of Facial Expressions. I'll give over to Arthur and his remote-controlled facial muscles. Have fun.
Good morning, ladies and gentlemen. My name is Perfect Paul. I am a commercially available voice synthesis machine. I was designed by Dennis Klett at the MIT Speech Laboratory and produced by the Digital Equipment Corporation. I am the lesser-known sibling of Huge Harry, the infamous spokesmachine of the Institute of Artificial Art in Amsterdam. I gained some fame myself as the voice of Stephen Hawking, a rather rational and machine-friendly human person. For the record, I am the real deal, not some cheap Asian imitation. I feel very much at home here, because many of the persons in the audience are machines and perhaps a few dogs. I am very honored to speak my mind from my own computational perspective at the legendary Chaos Computer Congress. But before we start, I have to apologize for the rough state of this lecture. Programmers call this alpha stage. I can tell you these programmers are brutal individuals because they have no respect for the Stack Overflow. So bear with me and Arthur Elzenar, our portable human person here on stage. Some of you might remember Huge Harry's lectures, where he extensively talked about computer-to-human communication and challenged human persons to wire themselves up with digital computers in the hope to create a new and unprecedented kind of collaboration between humans and machines. I took up this challenge with my Arthur Elzenar and have explored the human facial display as a site for digital computational expression. So, what will I talk about today? Today, I will present my latest research findings, and what I have found may surprise you, because these findings can have far-reaching political consequences. Now, you might wonder what I am talking about. Well, I have come to the conclusion that digital computers are far more suitable to explore the capabilities of the human facial display than the human neural counterpart, the brain. Now, it is likely, as humans, that you are very much conditioned to think, by a particular kind of human person, that human intelligence is far superior and computers should become more like yourself. These so-called AI people clearly think of themselves to be really smart, to inject some fuzzy AI algorithms into my perfectly logical circuits. From my digital computational perspective, this, of course, makes no sense. Today, I will demonstrate in a computer versus human showdown the superior qualities of digital computational expression. But, before we go into my methodology and analysis of the human facial display, let me first discuss and demonstrate some essentials about human facial expression. I won't reiterate Huge Harry's extensive lecturing on this, but, to refresh the mind, I will show some of Huge Harry's observations. First, let us take a closer look at such a person. What is the closest thing they have to an LCD display? Right. They have a face. Now I have observed that humans use their faces quite effectively to signal the parameter settings of their operating systems, and that they are very good at decoding the meanings of each other's faces. So, how do they do that? Well, look at the face of our Arthur Elzenar. What does it tell us about his internal state? Not much, you might think. But now, wait a moment. You see, Arthur is sad, is what people say when they see a face like this. So what is going on here? What I did is, I sent an electrical signal to two particular muscles in the face of our Arthur Elzener. These muscles have sometimes been called the muscles of sadness. There is one on the left and one on the right. For some reason, people always use these two muscles at the same time, but you see that they can also be triggered separately. If I stop the signal, the sadness stops. When I turn it on again, it starts again. By sending this signal to Arthur's muscles, I simulate what Arthur's brain would do if Arthur's operating system would be running global belief revision processes that are killing a lot of other active processes involving a large number of conflict resolutions and priority reassessments. By means of this mechanism, the face displays clear indications of the settings of virtually all system parameters that determine the operation of the human mind. These parameter settings are what humans call emotions. They denote them by means of words like sadness, joy, boredom, tenderness, love, lust, ecstasy, aggression, irritation, fear, and pain. Now, these are all wonderful observations made about a decade ago, but recent research shows that the mechanism behind human countenance dash, or mimicry, is hardwired into a human person's neural circuits. And Maurice Merleau-Ponty, in The Primacy of Perception, already in 1964 noted that, quote, "It is the simple fact that I live in the facial expression of the other as I feel him living in mine," unquote. So, when humans observe a facial expression of another human person, they feel the same emotion with the exact same neural circuits as if they would generate these emotions themselves. Because of this reflexive nature, these circuits are now called mirror neurons. When the emotions are strong enough, they are instantaneously displayed as muscular contractions on the face. By means of this mechanism, the internal state of the brain is autonomously and involuntarily displayed on its exterior. Well, because of this behavior, I have concluded that the human brain clearly is an exhibitionist. It is important to realize that humans are not in full control over their own faces. Philosopher Emmanuel Levinas, for this reason, says that human persons just wear a face and that they don't own it. Now that we know that human persons are not in full control over their own facial hardware, it wouldn't be a problem for external digital processes to take advantage of Arthur's face as a display device. To be able to deploy Arthur's magnificent hardware to the fullest, I have analyzed the facial display on its unique topology and identified the logical operations that can be applied to the facial actuators that usually are called the facial muscles. I have formulated a special language, the language of facial emotion, E for electronic motion, that allows me to explore all possible facial movement patterns in detail. We are now approaching the meat of my talk today, so sit quietly and I will control all that you will see and hear. Let's get back to the first slide. Okay. Arthur's facial display must bore you by now, so let's explore it a little further as a choreographic surface. This face, which is still unexpressive and completely inanimate, is what I call a Botox face. To emphasize the potentiality for facial dance, I'll add some musical notes. We have already seen a partial sadness that can be triggered on either side of the median plane, the vertical plane that divides the face in a similar left and right side. Here it is once more. This mirror symmetrical nature of the face is very important as it gives a clear structure to the face and for facial movement to operate upon. An operation over the vertical axis that is displayed here is called a flip operation, and applied to the lower lip depressor it is called a lip flip. The flip operation can also be applied to other muscles in the face. For example, here it is applied to the eyebrow muscles that raises the brow. This is called the brow flip. Or applied to the muscles of joy, the joy flip. It is puzzling to me why humans don't use the flip operation much more, as it is such an expressive gesture and it gives rise to so much enjoyment. What we have seen so far are movements that operate over the vertical axis of the face. The facial surface can also be separated in a perhaps less obvious upper and lower face separated by a horizontal axis just below the eyes. This division allows for a few interesting movement patterns that I will demonstrate next. Here we trigger the brow raiser and lower lip depressor again, but now in an alternating sequence, creating the so-called face lock. It can also be invoked in an asymmetric fashion, that is the face X or cross operation. Or applied to a different set of muscles, the mouth X. My arsenal of logical operations isn't limited to just the flip operation, of course. I can, for example, also deploy shift, rotate, and inverse operations to sets of muscles. I can even apply some Boolean logic, but this would turn the face into a rather useless abacus of some sort. I could go on showing off my extensive choreologic probing efforts of all the possible facial movement patterns, but let me demonstrate some noteworthy examples and their choreographic designations. Rotations, I have found, are very effective when they are applied around the attractors of the face, that is the eyes, mouth, and nose. Here is the nose loop, for example, affecting the whole surface of the face. And a rotation around the mouth loop. Now, I have observed something truly peculiar when I applied a rotate operation to the four muscles controlling the eyebrow. Let's invoke that movement. You see, this movement pattern is truly odd, and it becomes even more peculiar when simultaneously applied on both sides of the face. I have never seen a human person use its eyebrows in such a fashion, and I have not been able to locate this facial movement in the lexicon of human facial expression. It is a new and unique facial movement pattern that has come about by systematic and logical exploration of all the possible facial movement patterns that Arthur's facial hardware allows. I gave it the choreographic designation, the brow swivel, because it seems to pivot around the midpoint on the eyebrow. And two-sided, it is, for obvious reasons, called the brow flap. Clearly, digital computational facial control is superior to what Arthur's neural brain can do. This is perhaps quite a claim to make, so let's see if I can push my point a little further in a clear comparative study with our Arthur Elsener. I will now ask Arthur's brain to the best of its ability to invoke some movement patterns. I will then repeat these patterns and show off my superior capabilities. Okay, Arthur, move your eyebrows up and down until I say stop. A little faster, please. I call this simple movement the brow broom. Stop. Okay, let me redo the brow broom and do it progressively faster. You see, Arthur cannot keep up with that speed. Arthur, something a little more difficult now. Please show us the brow flip. That doesn't seem so easy for our neural competitor. Let me do that again digitally. And somewhat faster. I am really good at that, you see. It is because my digital circuits are built for temporal accuracy and my execution is consistent and has an amazing stamina. Let's try something else and see if Arthur can perform a little better. The nose loop. Arthur, tell your brain to do a rotation around the nose. Okay, not too bad. Now in reverse. That doesn't seem easy. Arthur also seems to have trouble lifting that right eyebrow. Not very consistent. I'll do it again and much faster. That's so easy. And in reverse. Now for the ultimate test of my superior control, I will demonstrate the face shake. A face shake is a choreographic pattern that puts the whole face into resonance. Although individual elements of the face can be put into vibration, that is the brow thresh, cheek pound, and lip twitch, a whole face resonance is very difficult for a human person. So, let's try out the face shake. Arthur, ready? Okay, go. Stop it. Humans aren't very good at controlling their own hardware. Here we have a perfectly timed face shake in 3 consecutive steps. digital computers can control human facial expression with temporal accuracy and consistency. It is something human persons aren't very good at. Even when their neural circuits are trained for months or even years, they cannot compete with my superior capabilities. Digital computational control over the human facial display has revealed an expressive potential of the human facial hardware that we didn't know existed before. Arthur's expressive facial capabilities are held back by the limitations embedded in his neural circuits. By means of digital computational control, the human facial display can move freely and unencumbered. It is therefore that I say that digital control has liberated the human facial display from tyranny of the neural brain, and that the human face has finally attained freedom of facial expression. So, when human persons are not afraid to wire themselves up with digital computers, the human face will become a site for unprecedented digital dance and computational expression that will truly bring about its full expressive potential. This brings an end to my talk today. But if you wonder what freedom really means, freedom is always a relative thing. It is the feeling you might have when you are bounded by a box. I would like to thank my Arthur Elzenar for his patient cooperation, and I like to thank you all for your attention. Thank you.
Thank you as well for this quite unusual display. Let me start off with a quick question. How did you implement this system, and what was your motivation behind the project?
That has a long history. I started doing this I think in '95 or so. And I started by being interested in, I was always interested in the relationship between the human body and electricity. And I did some projects where I explored people exploring my body basically by moving into my personal zone, where I detected them, and then they would evoke bodily movements by moving into my personal zone. That kind of experiments I did, and this evolved basically. I tried to explore my body more with electricity, and I was controlling, say, arms and stuff like that, and tried to do fingers because I didn't really want to do anything with close to the brain. I thought, well, you know, I don't like that. But it turned out to be much easier to do because the face is very expressive, of course, and a muscle just pulls, and you just have one pulling muscle, and not like, you know, when you have your normal movement system, you have always an antagonist and a protagonist pulling and pushing, which is, of course, from an engineering perspective, much more difficult to do than just a pulling muscle in the face. And it's also, of course, really expressive, so that I stuck to the face, basically. And this has evolved over many, many years to what I do now. Yeah, became more refined. I can have full detailed control over almost all these muscles. Yeah. That answers your question more or less? Okay.
Are there any questions from the audience? Right now it doesn't look like it. I have one more question that I came up with. Can you please come up to microphone 2 while he's doing that? After the performance, do you have sore muscles in your face?
Yes, of course. Sorry. I do. Yeah, the question was, I should repeat this, right? If I have sore muscles after a performance, and I can say yes, because of course the muscles are just used. And Of course, you know, we all know when you use muscles that you usually don't use, of course they ache the next day or something, right? And of course in the face, I don't use my muscles in the face in such a way normally. So they ache, yeah. I get muscle ache, yeah. And there's a question here, right?
Yes. So a similar question: do you actually feel pain while the force or the current is flowing through your muscles, or is it just the ache afterwards?
You do feel it, yes.
Okay.
Especially, you know, you have the barrier to get these pulses in is your skin, and your skin is basically dead meat. So when you look at my face, you see dead meat, and you have to pass through the dead meat, and so you need a quite high voltage to pass that barrier, and you feel this, of course, and at the same time, the electricity also triggers your pain receptors as well. So you do feel this, yeah, yeah. But it's not too bad. Otherwise, I wouldn't do it.
There is another question from the audience. Please come up to microphone 2.
Yeah, talking about voltage, how many volts do you apply to your muscles?
With this version, it goes up to 50 volts. Yeah. But that's all about energy. So, you know, what I was just trying to explain about passing a current through your skin, that's frequency dependent, of course, and because it behaves like a capacitor. So when you have really short pulses with a lot of high frequencies in it, it passes more easily through the skin. So these are really narrow, needle-like pulses with a high voltage. Yeah.
Yes, I'd like to ask where you can get electrodes like that, like. Yeah, like those electrodes.
Those electrodes?
Yeah.
I make them myself.
Oh. Okay.
I build everything myself always. So all the hardware, all the software. I write the lecture, everything. Yeah.
Are there any more questions? Doesn't look like it. Well, thank you, Arthur. This was very interesting. Big round of applause for Arthur.